Yeah, let's get started. Yeah, so we will today go to the topic of attention. So that this one gets to the transformer and the large language model. So these two lectures, 10 and 11, still a little bit mathematical. So there are a lot of notations. And then after that, there will be some which are easier. So let's talk a little bit about the motivation first, about attention. Yeah. So first we will talk a little bit about attention motivation just in the context of RNNs, which is where historically attention has been studied first. Then we will talk about high level of transformer. Transformer will also continue next time. So both really is for the purpose of a transformer. The high level, then we will talk specifically about the attention parts of the transform. Basically, there are two things which are in the original transformer paper. But it had self-attention as well as cross-attention. So basically, this will be the topics about today. Today we'll focus on attention mainly. Next time we will talk about the transformer more general. So we assume that we know the multi-head attention, so that we will not cover attention next time. So we're gonna try to focus this one. So we will talk about other issues in transform. Anyway, so this is a topic. And certainly attention is become very, very important. It's essentially the key, actually the key components of transform. And we will see what issues they resolve. The issue we resolve, we will starting to look back to the recurrent neural networks. For recurrent neural networks, we know that it can forget long-range dependencies because recurrent neural networks using this compressed latent state. We call it edge to compress the history, and everything is dependent on this compressed history. And there are fixes, partial fixes like LSTM, right? LSTM, we talked about that. It has a long short memory so that it will actually is less easy to forget long-range dependencies than the standard RNN. But nevertheless, they still use bottleneck, still use compression. If you compress something, something gets forgotten. So that has to be the case, no matter what you do, right? The one problem about this approach is once this information is forgotten, because it always produces compressed state, it can never be recovered. This issue actually, even in the more recent cases like LLMs, you still have a similar issue in the sense of in the following. So LLMs, you have a context, right? You have a chat history, and you keep talking with LLMs. And at some point, if you use all the chatbots, they were agent systems. They are all the same. Essentially, they will say your history is too long. Let's compress that, right? So they are doing something different compression than what we are learned from LSTM. But nevertheless, once the information compressed, you do see that some of the earlier information get forgotten. But for the RNN, because it's inherent in the model, there's no way to recover once you compress that. So this is essentially one bottleneck. And the main solution about this is just the attention, which is quite influential. You're starting with neural machine translation. At that time, translation was the target people trying to work on. Nowadays, this is regarded as soft, right? LLM can do translation arbitrary languages and not difficult, but at that time that was still very challenging. But they introduced attention to talk about alignment. That's in the translation framework. But for the RNN, we will talk about the key is our current use is really just this long range dependence issue. So this is just a quick, I mean, people probably could understand anyway, but we will just give an example. Let's say you have an article, you have the first sentence introduce something which is important, say navigate using Earth's magnetic field, which probably important for the context, but after this article goes on and on, at some point you want to generate continuation, right? Continuation, then at some point, if you have RNN, it tends to forget about already these very early things. Then when they do the completion, they only look at the more recent text. So initial sentences get forgotten, and then the model must recall. In order to do a better job, it must recall both the more recent history as well as the beginning of this sentence, the so yeah, basically the point of that again is just say, I mean, RNN, LSTM, they struggle because the hidden state will only contain more recent. They tend to forget a long history because of summarization, and once they forgotten, it will be very difficult to recover. So this is just an illustration, but you know, this is basically the point which we want to address. So mathematically, we could try to see that when we have a token sequence, right? So and the goal is to try to predict the next token, which is yt minus plus 1 from t1 to yt. We always through this hidden state, right? We update the hidden state. The hidden state can be considered as a compression of all the history from y1 to yt. This is a compression. And then once you have that, right, so you will learn from yt plus 1 using this all the history you have seen so far, basically, as a compressed history. It's not the real history, it's just a compressed. And this history is recurring, which means at any time something got lost, right? The next state here will always got lost. So you never recover. So basically, this is one problem with recurrent. Recurrence, although in theory you can claim you have infinite context length, in reality, once you compress, it tends to remove things which cause a problem. So this long range dependency, which means even when you read stuff, right? When you try to do whatever, like a chat with LLMs, at any point you may want to reread or relook at the early information, Y1. Because the sequence is coming from Edge, which is a compressed version of all the history, so you will not have any direct access of your Y1. Now, what attention is doing, right? Attention is doing is just say, let's have a direct access of Y1 rather than just depending on this compressed history YH, right? So it's a really somewhat like a memory retrieval system. Try to retrieve your memory from much earlier in your history instead of just looking at summary. And this is definitely things we will make a significant difference. So yeah, so basically, yeah, this is just say, instead of looking at this guy, right, as all your history, you want to have a direct access. So in the attention, just like a direct access from Y1 to this. Okay, so how do you do that? right? So this is what we want to say, and the topic of this lecture, right? So basic idea. So the basic idea of this attention, again, it's a direct lookup. How do you do the direct lookup? How do you create some kind of a memory system to say, I can, at any time the t, I can try to do any past history like HJ, right? HT is my current state. HJ is the earlier states. And then I would say I find the similarity score. Basically say something is similar about this state versus earlier states. And then I use weighting about earlier information. So which is something like this. So this one gives a weight. The weight is say it's looking at history and current, whether there are some similar patterns appear. SHTHJ will be the similarity of the current state, which is HT, and the earlier state, which is SJ, right? And this attention score, again, if you look at familiar, we have seen that multiple times. One is softmax, right, in the classification heads, or the other one we see that is in the contrastive learning, which also use this similarity based. So attention, if you recall that attention, when we do the similarity based, we try to look at close related to be more similar, right? The other one is less similar, using exactly the same kind of expression. Here we use that just looking at instead of just distinguishing, doing representation learning, we really look at using this as try to look at which in the history we should pay attention to. So this is basically what attention is, the weight is, and then what do you do with that, right? Now what you do with that is because okay, let's say HJ at some point is a compression of your history at that point, right? When it's close, HJ is a good compression, usually. Once times goes long, when J is far from T, HT will not be a very good compression of some very earlier states. But HJ could be a good compression at that time, at that particular time. So when you do say, oh, this my current state is close to some earlier state, say HJ, then attention weights like this guy will be high. And then I will copy these particular weights. I'll boost these weights so that I remember things which from the earlier state. I'm recalling the history. And then this is a combined history will be my new so-called context vector, which can be used for prediction. So this one is a better summary of history than my current summary. My current summary is always lossy once it goes very far. But this summary will try to have a direct lookup at earlier states, right? So you always look at directly earlier states. Therefore, if your attention gives a high score in the early states, you could recall. So basically, this is basically intuition, yeah, about how this attention is doing. And then you can use this guy to actually do this attention. Okay, let me. I think so okay, so this is essentially the key idea. Try to capture language dependent with the most relevant. Now let's look at the illustration. So another one, right? So this is a history. So memory. So sometimes we call it memory. Generally, attention is a memory mechanism. So memory retrieval, which later we will also see a different, more general form of attention, which use the transformer. But let's say it's a historical information you are saving in your history states from H1 to HT, right? So each time state, again, as I mentioned, usually when this H1 is closer, it have a good compression for the tokens close by. This guy has good compression, tokens close by. This one has good compressions, tokens close, but not necessarily far away. But then once you have this weighted combination, you will be able to access anything in early. So there's a sum to be 1 condition, right? Because this is a softmax, so essentially sum of alpha is 1. And basically, this is a way of recalling history. So, and this is essentially the way about saying that we are saving everything in the memory, and then we will retrieve that when needed. And the retrieval is based on this guy. And later on, we will see that it's a more general form of attention, which also is in the transformer, which using this memory system point of view. One thing about it is a similarity function. In the transformer, in whatever, usually you have this so-called scaled dot product. This scale, this one is HT H prime divided by beta. So why we want to divide beta? We'll say it again later on when we look at transformers. It's because we want the range to be reasonable, right? Range to be say -1 to 1 or something. You do not want this. So usually beta is a square root of b in the transformer. We'll come back to that. And this one, you just say this range you do not want. It's like temperature. Even in the contrast learning, you have temperature. The idea is to want to hopefully the typical range of this score when normalized is you know, it's constant, like -1 to 1 or something, or -2 to 2 or whatever. But it cannot, certainly shouldn't be 10, 100, right? So that's too large. Too large, then it will cause a problem in this. Basically, it's too peak. That is very difficult to train. So you want that to be a little bit smoother. So this is where this guy comes in, especially in the beginning, when you initialize. This will come back to that. So this scaled dot product, the scale in the balancing the range. And yeah, this is generally the formula attention. So let's look at the example. This is just an illustration. You just say, oh, I put more attention weights to, these are probably more indicative to predict this dot, right? So I just want to say, this one give more attention weights, and then you can give all the weights to every words, but these are probably the higher weights, which compared to what? So attention to, essentially you can look at attention map, the weights, how large it is. You say how much attention you are paying to each word. This is a more general view of attention, which is what we actually look at both in the transformers and in the general memory system. You can, from this view, somehow you can view attention as a differentiable memory system. It's a retrieved memory, and the usually memory, this kind of memory, typical in the machine learning, it's a key V memory, right? Key is a key, V is a value, and this one also use a lot of in the data processing. A key V is a pretty basically you're matching the key, retrieve the value. So that's the typical. The matching, of course, you have a matching score. You can either exact match. If you have a string, you can say I exact match the key, and then you retrieve the corresponding V. Or you can have an approximate match, right? So in our case, for the attention, it's more like an approximate match. Approximate matching the key, and you have sum over your V, weighted combination of V as your retrieved map. So this is essentially give a query. Query is basically a vector. So this is SQK, right? Is similarity between query and the K. The higher the similarities, the more similar they are. And this one, as we mentioned, it can be a scaled dot product. So the dot product, we could also use cosine in the. But cosine is a little bit harder to work with in terms of differentiation. So the scaled dot product is pretty common in the rather than cosine. Cosine was used in the contrast learning that paper, right? So, but this one we can use dot product. So this is a similarity between this query and query and key. We want to retrieve a context value out of this. So basically, context will be a combination of B, right? So here is a formula. So this one again is an attention formula, which basically say it just given the weight to all the keys which are close with high similarity to your query. So the higher the similarity, the larger the weight. And then you normalize that. Normalize so that sum to be 1. These are key, and then you give us weight, right? Using the same weight, that you can do a combination. So memory is always key V. And here, instead of retrieving a single value from a single key, it's a mixed value of a mixed key, right? So basically, it's a weighted combination of your value, and the weighting is based on how close your key is to the system. So you can think about that as if alpha I, one is very large, right? The other one is 0, one is very large, then one of the alpha I is 1, the other will be 0. So you are retrieving a single key, the value associated with a single key. So that is the typical memory, retrieve a single value correspond to a single key. But here is a differentiable because you have a softmax. This one becomes a smoothed version of a memory retrieval. So it's a smoothed value, and essentially this one works quite well in general. And all this comes back to be you need a vector representation, right? So each Q usually is a vector. V will be vector. Somehow they can be additive. A lot of representation learning is this V has a similar semantic space. Somehow they are additive. So when you're adding that, still goes back to some similar semantics. So here they use this kind of interpretation, and then basically you are saying the weighted average of your values will have a meaning, semantic meaning. So and then this is the system. Okay. So anyway, so this is general attention where you give a query, you search for the keys, and based on the different score of keys, you give weights for those keys, and you do a weighted sum of your corresponding value. So KV system. Here's a PyTorch for the general attention. This using the batch matrix multiplication. This one basically you're starting with a batch, which is always because in the PyTorch we always the first dimension will be the batch, right? So, and the other one will be some the dot product, and then essentially the this one keys will have M keys because you're looking at here, right? Your memory, each of that respond to memory. So usually query just one query, which say of D dimension. This one is M of your queries, M of your key value with a D dimension. So you do a transpose, making D is here, then you do a matrix multiplication. Essentially, it's an inner product sum. And then you have a scale. This is a scaled dot product. And then basically, this alpha is the softmax, right? It's basically you give that, pass through softmax to get your alpha. And alpha becomes shape is batch and M. And then you have values with a batch M, and you just do a batch matrix vector multiplication, which basically becomes this one gets there becomes 1 d dv, and then you squeeze 1, which makes it essentially the context view d dimension. Okay, so roughly this is just implementation. You can take a look, or if you're not interested in the you just look at what it produce. Basically, it's a given query and the batch of keys. It will have weighted products, weighted sum of values, so that it will return your products. Okay. Let's talk about the attention. Then we will move to the transformer. Transformer is using this attention to the extreme in some sense. One thing, okay. So there are a couple of things, right? So one thing about the traditional RNN, we mentioned one limitation. Actually, we mentioned both. We this time we mentioned this long range dependence, and before we mentioned this guy, sequential training. RNN is like very deep neural networks. You can think about the one you're going through the backpropagation through time. It goes through a context length of that long, and then basically, tokens are processed one at a time, limiting parallelism. This is for the training. For the inference, you always process one token at a time, right? So, but for the training, this causes a problem. Long range bottleneck. This one we just talked about, right? So information passed through a compressed hidden state. We know this guy actually can be resolved using this attention. So this we just try to say the number one. So what about the number one? Right, number one turns out the transformer just to the extreme in terms of sequence modeling compared with RNN, right? They want to say first they wanted this guy, right? So certainly if you want this guy, you need attention, right? The question is, do you need a recurrence, right? Because in the typical RNN, we still have a recurrence, even you have attention. Here, say if we want to achieve that, we cannot have a recurrence. At least the nonlinear recurrence. And nowadays there are more complicated recurrence, linear state space model become popular because they can have some kind of deal with this problem. But for the nonlinear standard RNNs, if I have recurrence, this one is has to be there because there's no way to simplify. So attention is get rid of the recurrence. And the purpose of that is just say this one can be resolved. Training parallelism. So they introduce so-called self-attention, which we will talk soon. When you do the self-attention, essentially you can compute all the interactions simultaneously because there's no recurrent to have one at a time. Therefore, it can be all computed simultaneously. And this is it doesn't save flops, right? The computational complexity in terms of flops, the floating point operations it doesn't save, but what is saved is parallelism. So basically, you can train efficiently between GPUs, which have a strong parallel, while sequential you can't. So this is actually the purpose of that paper. You say there's direct dependency modeling. This resolve this guy by using attention, right? So essentially, self-attention serves two purposes. One is it's a direct long-range attention, and they realize that as long as your range is good, right? You do not need a recurrence. You do not need a recurrence. So this is where you can achieve that. So that's the key. Actually, all the nonlinear dependencies among the tokens are achieved through attention. So and there's no recurrence. So that's the key about a transformer. So the original paper really promotes this as way of parallel. Okay. So let's talk about and also they make I think they are the first one to get multi-head attention, which turns out to be important. And we will talk about that. The original attention in the original paper, which we mentioned, which was in the original paper, was single head attention, just a single attention. Right? But later on, they extend that. Once you put that together, multi-head attention, and get rid of recurrence, it's very natural. The way of transform. Well suited for long term. The other one is what's interesting is this particular architecture scales very well. So that why there are very huge transformers, right? Because we'll talk about scaling law later. Just talking about it. It turns out to be when you add parameters to that, it have more capability. So you just keep adding parameter, keep scale. So that's another thing about the transformers, which are kind of interesting. Some other architectures will be more difficult to scale, even like RNN and so on. So it could be more difficult, both computationally and I think parameter wise. I think they are related, these two. But anyway, so these will be the things which are important for the transformer that becomes the current architecture of choice for many problems. And they start again with the machine translation. So we will talk about this machine translation setting, right? The original paper transformer, basically, I think everybody knows that paper. Its attention is all you need. Is about machine translation. So this one is I translate the English to Spanish, right? And essentially, remember they still have this point of view at that time. Now we can discuss more later on when we talk about the different transformers. They view that as encoder decoder. So the original paper has this encoder decoder. And encoder certainly, as we mentioned in our encoder decoder structure, encoder will actually be embed your data into some vector. In the case of transformer, it has sequence of vectors. It's not encoding to a single vector, but a sequence of vectors. And a decoder use these vectors, try to decode your sentence, right? LSTM give you HT will be. But the attention, because they can go to earlier stage, so they actually keep all the hidden states. So basically, this is what it is. So you have encoder decoder, and we will talk about the difference of encoder decoder in the transformer. There's a clear difference, which is important. We'll state that. So you start with forming these hidden states, right? So basically, in the encoder, it's so-called bidirectional self-attention. Self-attention means just looking at these particular nodes, right? They parallel to all the nodes, all the hidden nodes. But these guys try to do the self-attention to all that. They all computing simultaneously. We'll give the formula later, but essentially they all computing simultaneously. Inputs, all of these are computed through attention through everything left and the right, both. That's the encoder. Encoder's attention is from both left and the right, because here is already given, right? So it's so you can do that. And then we will form another one. Let's say this is a top layer. Then we are done. Okay, so there's a two layer. You could add more, but this one just tell you each one you have attention is coming from left and right. Now let's move on to the decoder. Once you have to decoder, this sequence of vectors, H1 to H5, will be your encoding output, basically your representation. If you have LSTM, you just have this guy. But if you have because we are doing attention, so we will have all. Now for the decoder, it's the same, right? So you're starting with hidden states, which called S to differentiate from the encoder states. And then what you do is here, right? When you do the attention, you're actually still using self-attention here, because at this decoding state, you only generate this guy. You have not generated this guy yet. So you can only attention to the left, which is a causal attention. You cannot attention to the right, because the right hasn't been generated yet. You generate one token at a time, okay? So the soft attention is always a causal attention to the left. This is the decoder state is always regarded as a causal. This is called cross attention, which is attention back to our encoder top level representation. This one is a slightly generalized LSTM, because LSTM, I mentioned that you're starting with this guy. If I have attention, I can attend to all of that. This one is using attention, okay? So you have a self-attention, you have a cross-attention. Cross-attention is pretty similar, so we most focusedly talk a little bit about the self-attention and for the transformer, which is here. And then when you do the cross-attention is here, right? And also there are something called attention mask in the transformer. there are later on we will say there are more purposes, but for now you can think about that as either causal, which is for the decoder, because decoder will not see the future tokens, so it's a causal, or it will be bidirectional. That's for the encoder, because encoder already see everything. Okay, and they are treated as two different. So encoder bidirectional, and this is achieved through attention mask, which will decoder is a left to right. Okay, so now you're forming. I mean, this one is just again using this particular state as one, but you do that simultaneous. Actually, decoder you don't do the simultaneous. It's really yeah, it's a really the thing. So and then you do that. You can do that in the training and the test. I will comment on the parallel training part, right? So the test you generate one by one. Training, you just need this causal attention so that it never depend on the future. But all these states can be generated simultaneously, because in the training you do know both this one and this one in the training. Therefore, you can actually compute everything. It's just your attention map has to be observed to be causal. Okay, so therefore in the training, similar to the encoder, which because you know everything here, you know everything. This one just shifted the prediction, just shifting by one token, and essentially you can do everything in parallel with attention to left. This one you can do everything in parallel with attention to both directions. Okay, so this one is essentially the difference of encoder-decoder. Its only difference is the attention map, the attention, so-called attention mask, which is either causal or it's bidirectional. Questions so far? Yeah.
For the bidirectional, you still generate one token each time?
Bidirectional is encoding. You already know the source sentence assume is a given. You don't need to generate, right? So you're given English. Let's say your prompt. Your prompt is given by user. So you do not need to generate one token at a time. You just form representation. You can think about in the older design, the encoder is your prompt, encode your prompt, and the decoder is the generation. Nowadays, people don't do this anymore. We will comment, but in the future, to say, right? Yeah.
If I remember in BERT, it's like you mask something.
BERT. Yeah, BERT is an encoder. Yeah. It will. We will talk about BERT later. But then this one is not one token at a time. This one is already even for the encoder. Okay. So therefore you do it by. This is actually the key difference: bidirectional versus causal direction with the encoder decoder. Okay. I think there's very little other difference. The other one is the cross attention. Is the decoder always refer to the encoder, the top layer, right? So that's why. For all this one, they actually use this layer itself. Self-attention here, this self-attention, they all looking at the same layer, and they achieve parallel. So let's take a look at this layer-wise. This layer-wise is just the input layer. Right, there are so transformer layer, and we will talk about transformer layer. This transformer layer has two components typically. One is the attention, another one is FFN. FM we'll talk about next time. So today we'll focus on attention, and attention is through this either self-attention or the cross-attention, but we will focus first on the self-attention for this, which you can look at either decoder or encoder, but essentially. Looking at this transformer layer, they has to form the attention to it, and this transformer layer too, and then you can describe, right? So basically, this is how it works. It's layer by layer. So besides the input and the output, everything is very similar. It's just a transformer layer. They all look very similar. So basically, they are the same thing. It's just different parameters. They do not. You could, but they do not usually share parameters between the transformer layers. But they are each one is very similar design. You just add them together, then you get one. Okay, so let's take a look. All dependencies are captured by attention. So that's the key, right? So if I remove the attention, then every token just work on itself. It doesn't, for the FFN later, they do not introduce additional dependence of token. They just work on specific tokens. But all the dependencies among the tokens, the sequence, they are just attention. During training, the key is everything can be accessed in parallel. We will see the formula to say what is the parallel. They in fact they just a matrix multiplication. All you need is matrix multiplication. During the inference, of course, we do that one at a time. Okay, self-attention in token-wise representation. Basically, I will just look at a single token, right? I, and then we'll see what self-attention looks like, and then we will make that matrix formulation so that you can see they can do in parallel. So you have input. Input is coming from the previous layer, coming just the output of the previous layer or out of the input layer. It's you have a dimension so-called D model. This is the dimension. It's just a representation of each token. You have L tokens. Each token is a vector representation of that particular token. So you form a representation of every token, and you have L, right? So this is a sequence length, and you form a key V. Remember, we have this memory system called the key V, Q key V, right? Key V is a memory system. This is the history. Key is your token times a matrix. This is a linear, so it's a linear form. V is also a linear. It just have a linear parameter. These are model parameters, right? So basically, this is a linear projection, another projection, and the Q is another linear projection, which is a query which try to match with key. So Q key and V, we will use exactly the same formula which we used before for the memory system. Using the attention. So here is attention calculation, right? This is the scaled dot product. This attention mask, which we will talk about that later, attention mask. But for now, you can say it's a 0. But essentially, you know, this one is your similarity of Q, which is a query, and the key, which is your key, your memory, key V system, right? Key V, and the square root of D. Square root of D is designed so that if you're doing this as a Gaussian, this one has a good range, right? I mean, if this is a Gaussian, then you know that the standard deviation of this guy will be 1. It's still a Gaussian, will be 1. So this is why you use the square root of D. Okay, it's make the range to be manageable. So that's in the initial. And then you're starting to train easily. And once you train easily, you can get more specialized later on. But for now, this is basically what it looks like. So and then of course we just adding V as your output. So that's all attention is doing. So attention layer just at this. This is just but this is the most important part of transforming somewhere. Actually, I want to say it's not necessarily the most important, but because FFN is also important. But then, you know, this is the key about all the interactions. How do you get all the interactions of different dependency of different positions is through attention. Basically, there's no recursion. It's just attention. Okay, and these are output of your attention. So this is a standard attention, but it just you have a single input representation of each token at the beginning of every layer. They try to form QV key, and they try to do this mixing, and then they output another token representation in the DV. It's another dimension. Later on, we'll talk about how this merge together with the dimension in the. I think that will be the next lecture. But nevertheless, this is coming with a certain dimension going out with the V dimension, right? Is your value. Okay, so that's all about the attention. Now we can say this one can be written in the matrix form. So this is where the parallelization comes in. You have an input. You have L tokens. Each token is a D dimension, D model dimension. So therefore, you can form that matrix. Also, you have a batch size in the first dimension. So it's a like 3 dimension is one of batch size. You have L, then you have D, right? So basically, and then you have these are the rows. These are the rows. Okay, so each token representation, and you have model parameters. This guy will be the dimension. Yeah, basically, this one project to the key dimension. dk is the dimension of your key v, right? Of a key and a query. Key and query they share the same dimension because they need to do dot products. So each one project this guy to be starting from a model dimension to the dimension of keys, and also query, right? This one is a dual projection. This is just a matrix notation. It's the same thing which we are looking at before. It's basically say you are going to a dv dimension. So it's a v, okay? And then you do this attention mask and do attention. The attention formula will be row-wise softmax over your whatever. And then the softmax and the QK transpose turns out to be L by L. It's like an attention, full times attention. And this one is a bidirectional attention. How do you do the causal attention? Using the same thing, but using attention mask to achieve a causal. So right now it's a L by L. So every token attend to every other token. It's a self-attention. And then this one is parallelizable because it's just a matrix multiplication. This one is an additive attention mask. Basically, it does the following. So if I don't want these two to be attended, for example, if I do not want my current token to attend to a future token, then I will put a very negative n. Negative infinity or very large negative number, 10 to the minus 10 to the minus 10 to the 9, something very large. When you have a very large negative number, if I do a softmax, it becomes close to 0. Essentially, it makes the softmax not ignore that attention. And usually they always additive. This is the implementation. The standard implementation always using this additive attention mask. The reason you want to do that instead of you say, oh, I waste my computation outside because you just want to use the standard matrix multiplication. We do not want to mess up here because we know the algorithm which can be parallelized using GPU, right? And then you say I ignore something instead of say I do not compute here, still compute here, or just add a very large negative number so that this one can get ignored in your softmax computation. So for example, all the future tokens will get attention mask, negative infinity or very large negative number. And the effect will get ignored, okay? In the encoder, because of a bidirection, so everything is 0 because you don't need any attention mask. But in the decoder, what it actually is, you have negative infinity or large negative number, actually. For example, minus 10 to the 9, minus 10 to the 9. So this is attention mask. And this is generally how it's been done in this setting, so that you still have the matrix multiplication, which is always LD, right? LD, right? So you're always doing this particular matrix multiplication, no matter how the attention mask works, but then you mask out some of the entries. And this achieves the parallelism, make it parallelism. So this computer for all parallels using the GPU, and this is why it's designed this way, why you have attention mask. Okay, and additive, why it's additive. But basically, all I'm saying here is you look at a single attention, you put that together, you become a matrix vector multiplication. This one you can work out the math yourself, just try to see, compare with the single one. Single one is pretty standard from the earlier. But this one is more compact form, but then you have to try to map out. But essentially, what I'm saying is this one works out. Okay, just like that. Parallelizable formulation, and that. So here is, basically attention mask, right? So if I put a very large number, right now, let's say I have the 3. This is this position. First, I will feed PV. PV is a projection of X, right? And then I will also form Q, right? But I say, okay, I want to also attend to previous one. I don't want to attend to the future one. Then what I'm going to do is making mask here is a very large negative number, such that to induce this to be 0. Okay, so this is how it works. And then you output it with attention weights, right? So basically, this is the standard attention. Essentially that's so-called self-attention. Self-attention, if you look at it, you just apply the attention to the input representation of each layer, and then using the projection of linear transformation of a key V cube, right? So and then you do a parallelizable. I think one thing they realize is parallelizable. So that's of course it's easier to see that in retrospect it's just a lead vector, but then you have to be able to recognize that, and then there's no recurrence from here to here, right? So if you have recurrence, you go to here, there's arrow, go to here, arrow, but there's nothing like that. So this is attention. What we want to say a little bit more about is block the invalid position future token, and so basically weight is 0. Okay. What I want to say a little bit about that is also that. I think we already mentioned that, but this one just repeat is up here. It's a little bit redundant, but just saying it again. So they're actually beside the attention mask. Usually when you work on the this one will again come back to that later on, attention mask. What you typically in the decoder causal attention, the future tokens will be masked in the decoder. The other one is padding token. Padding token is a follow, right? You want to pad everything the same length. The reason again is this tensor multiplication. Batch is the first dimension. L, if you do not have the same L, you have to create additional complexity. It's possible to do, but it's troublesome. So in the standard formulation, like Hugging Face, whatever, they try to pad everything to the same length. Pad something for the same length. For example, if your sentence is not say you're padding your token your context length, for example, is 512, right? And then your sentence is 200, right? Then you have to pad more than 300 to be padding, to be something like so-called padding. But those padding just say it's an invalid token. Usually ignore that in the attention calculation. So basically, padding tokens. This one will come back to that later on again. And in the future lectures. But essentially another way. So usually you have two type of masks. One is decoder. One is padding. So that's a very typical mask. Okay, so we after that, now we can actually look at the multi-head attention. This is something created in this transformer paper, which is important, which makes attention powerful. Single head attention, if you think about it, focus on one thing, right? Just one part of the sequence. Sometimes you need to focus on multiple different type of sequences, have a different information. How do you do that? You cannot do that single attention, because a single attention, they give a fixed set of weights. So they want variable weights with focus on different part of a sequence. And this is where multi-head attention comes in. This splits, this inputs the attention into, each one is one attention. Basically, each attention, if you remember, you have a single W, critical Q, Single W correspond to key, simple W correspond to value V, right? So there are three matrices are the parameters for each single attention. And then you just repeatedly multiple ones of those learnable parameters. Each one have these three. So each head have three learnable parameters, if you recall in the attention. It's a WQ, WK, WV, right? So those are the projection to QKV. Because attention, once you fix the QKV, they are all fixed. So there's nothing else to learn except this projection matrix. Each one have one. You have another one. You have another one. And once you do that, you form output from this attention, output of this attention, out of this attention, right? There are three vectors. You concatenate these three vectors as your output. Then you do another projection. The projection gets you the same dimension of x to x prime. Hopefully you get the same dimension because that's the design they want that case. So x and x prime eventually have the same dimension. After your concatenation, this projection just project this to the dimension. Okay, this is another parameter. So in addition, okay, so how many parameters you have, right? You think about each one have three. So if I have three, right? So it's a 9 parameter matrix. And here projection is another matrix. So you have 10. So right, each have three. And the 3 times the 3 heads is 9 plus 1. So that's the total number of parameters you have for this multi-head attention. Okay. Yeah, projection ensures that. I mean, even this one can be the same as this input in many designs. Projection is still useful, just project another projection back. So why multi-head is useful? Basically, if you think about I mentioned already, if you think about this single head issue, it's actually just can attend to a single. For example, just attend to if you have extreme attention, just attend to one token, right? But you may want to attend a few things. So this is where multi-head allow to focus on different parts of sequence simultaneously. Then you combine the different information, and this one is clear improvements. And you multiple times of relation between tokens. Yeah, essentially this is the point. You want multiple relations. So different heads learn different interaction patterns, right? So and there are people actually study what these learns. Different attention heads learn, and then they can come out with some interpretation. Different learns actually some different things. They have different patterns. And but then they together with richer information. So this one is definitely using the attention mechanism, but make it such that it actually is more powerful. This one is make it sufficient to model the sequence. If you have a single head attention, usually it's a more trickier. Single head, I mean, in the transformer, you still could model different side because you have a different transformer layers. Different layers could focus on, but this one is more effective. Just same layer to model different parts of the sequence. So that's the purpose. And mathematical formulation, right? So that's basically pretty much the same thing as before. So we just we can quickly go through that. Again, this is input representation is a matrix. For each head, you just compute this. This one can be done simultaneous. So you just have this a head's attention, right? Solve this guy plus m. M is attention mask. And for each attention is this formula we already mentioned. These are all matrix multiplication except this softmax, which is also standard. But basically, these are parallelizable. And this sequence, you do a projection, you do attention, and the multi-head is concatenate this one, and you times this guy. What is the size of this one, right? Each one is L times dV. dV is the value, and this one becomes L times H times dV, right? Because it concatenate in the direction of dV, right? You align with token. You always align with token. So each token is aligned. So basically, yeah, this one becomes H times dV, and WO. So what is the shape? It should be H times dV to D model. Actually, yeah, a lot of applications, dV will be D model divided by H. So there, this one is like a square matrix, but it's still there. So basically, that's all your model parameter for your multi-head attention. So model parameter, you have Q, you have a P, you have a V. Those are projection matrix, and then you have H of that, right? So that 3H times 1 output. So that's basically forms all the, and they are all basically linear algebra. So if you look at that, everything is kind of a linear algebra, just to matrix multiplication, and that's all you need for the attention. I think that's about it. We want to talk about again there's a little bit of heavy notation in the linear algebra part, but hopefully you understand the basic idea, and you have to go back to map that to be a little bit more careful about the linear algebra notations to map that. I just want to talk a little bit about the cross attention, but they are basically the same idea. So they're not too much. It's just not self. You have to go into elsewhere. So yeah, encoder decoder transformer, right? Decoder needs two type of attention. One is a left to right, right? So we know that's through self attention with a causal mask plus causal self attention, and the other one is from the entire source sequence which are given. Here is what it does, and using the same formula for each position, you have this guy, right? So it's a this basically says I form Q key V of my encoder. My decoder Q is actually doing the product with a key of encoder, all the positions, and sum over V, right? So basically, this is an encoder length. So essentially, it's an encoder. Yeah, it's a encoder decoder structure. You have a cross attention, and instead of doing self in the decoder, if your encoder equals decoder is a cell, right? Decoder you just encoder equals decoder. Otherwise, it's cross. Cross is a very similar. Cross is very powerful. A lot of things actually starting just using cross attention to do, including any other information. So that becomes pretty standard. Cross attention is just forming nonlinearity, dependency of your what you want from whatever you need and the source. Here, query comes from a decoder, and key V coming from the encoder. That's what it is. You can write it in matrix. Again, this is just for your information only. You have to come back to math. But basically here is you're writing the H, right? So basically this says it can be parallelizable. You write the decoder sequence, right, as a state. This is encoder state, and define the projection and so on. And then basically this is a matrix form. It's of the same form. It's just key V now instead of using the instead of using the self attention, it's encoder becomes the encoder attention. So if you look at the shape, this one becomes decoder times L encoder. So it just the shape is different, and then that's all. Yeah. So and then you form this guy, and then basically that's all you have. So essentially, this one just quickly come. If you understand the self attention, this one is pretty easy to understand. Just the matrix needs some work, but this is for your information. Multi-headed, you can still using multi-headed cross attention, right? The same idea. So the idea you're just repeating the same idea over. Just you need to come up with notations, but otherwise, you have a different attention head to your encoder, and then you form that together. So basically, that's about it. So multi-head cross attention is you combine the cross attention heads, and then you do a output matrix, so you get your current one. Again, I mean, in this case, each one you focus on different alignment setting. So multi-head attention. If you think about multi-head attention, right? So you cross attention, you can use that for many other things. It's not only for this transformer, but you can plug in other architectures. This is used quite a bit. So eventually, you can think about it essentially, as long as you can map your source information, any information you want to be a sequence of vectors, you can apply this, basically. You only need a sequence of vectors to apply this cross attention. Okay, so let's summarize. Then we will probably quickly go through a little bit about this code, and then that's all. So one thing I just want to stretch again is there's no recurrence in transformer. It's solely on attention to model interactions among tokens. Right. So if you say we all know like they were pre-transformer very good to capture relationship of different tokens, right? Or different dependencies, sequence model. But all is attention. So there's nothing else. And so attention is the key part which in the sequence modeling capability of a transformer. So that's the key part because there's nothing else to model the interactions. And attention therefore is kind of important. So people try to play to improve the attention or modify either way or one way or another. But the original way, as we are describing, is still pretty standard. So encoder basically you observe that before you do the encoding, it's a source information which you already observed given. It's like prompts, like translation the source language. It takes token embedding as inputs and stack multiple layers. We have seen that. And each layer apply a bidirectional multi-head self-attention. Also, it does have FFN, which we'll talk about next time. And the top layer, this one is all the modeling of your interactions for tokens. Produce one contextual representation per token. So it's a one vector per token. So this is what you actually it's of the dimension of a D model. A D model is a dimension typically you're given to. This is one. Decoder, you have inputs, right? The outputs when you do the training is always shifted by one token, right? That's the same for all the sequence you have seen, LSTM, RNN, transformer. They all using the same representation. You shift by one token as output and inputs. Each token first applies self multi-head attention. Then you actually apply that in sequence. So you apply 2 times. So they don't mix that together. You just first apply. We will talk about that next time, basically how that. So you first apply the causal multi-head self-attention. Then you apply the multi-head cross-attention. If you have a decoder only, actually it's simplified. You do not need to have that. So all the LLMs nowadays are decoder only. So there's no encoder. So basically, this guy is not needed. But but if you have an encoder, then first decoder, then this one. And the final layer, then you just use the predict next token. So this is your final representation. And that representation will be for your next token prediction. And then you generate the logits. And these logits will be come to be decoded to the max softmax to be your token. Right. And the computation, remember, all you need to parallelize them because token-wise interaction is attention. So attention to be parallelizable is important. And we see that it becomes a matrix multiplication by linear algebra. Therefore, tokens each layer can be generated in parallel. All tokens together. This is for training. For inference decoder, you can only do that one by one. So that's what it looks like. Anyway, just quickly go through this. It's not too hard, but then they require a lot of notations. So basically, it's not too hard to write, but you need to the linear algebra get it correct. So here you just say, I mean, this guy are the linear layer, right? So basically, yeah, this is a linear projection. This one is another linear projection, right? Number of heads times this guy to this get to the dimension, because each one have m heads, right? Basically, yeah. And the forward to do is we can take a look. Forward is basically you first do a projection. Your you are actually let me see where you yeah you xq should be the same as xq basically here. I think it's just x. Yeah, everything is x, but this one is more general. This one written in a more general way. Just making it all x and x, and they are all the same. Oh, for the encoder one, this could be different. Depends on how do you view that. If you have a different modal direction for the encoder and decoder, then TV will be the encoder, and that is the Q is different. So it could be different. But generally, you do a projection, and then this one reshape to the heads. Basically, you separate it into H heads after projection, right? And for each head, you have different attentions. Actually, if you look at this one is really just one single. It's the multi-head, single head doesn't make difference. The only difference multi-head, single head is coming from the attention calculation. And this guy, you also you're the inner product attention, right? So here it's inner product. Then you are doing adding the mass. This one is a large negative number. If you want to ignore that, and then you do the softmax. Softmax gets you to the attentions, and then you do the with V, which gets you the attention out. Right. Then you concatenate this together, and then the basic output is your projection. This one to your output. So finally you get that. The main thing about this one is it's not a long code, but you need to know the linear algebra. You also have to match the dimension correctly. So, but this one is one of the code, so it's not too long. If you write that, you just need to make sure everything matches. Otherwise, you could have wrong dimension or something. But otherwise, it's just few lines of code. Yeah. So basically, this one gets your output. It also gives you the attention weights sometimes. Anyway, so that's about it. Oh, sometimes people also doing the KV also get you back, because one thing is they are so-called KV cache. I also quickly mention this, because if you are thinking about doing the decoder or whatever, right? While you do the decoding, KV they because it's a causal, you never change when you goes from position to position. So therefore, you do not want that to be recomputed every time. If you do this is for decoding, this one is for training. For training, you just compute it in one shot. But for decoding, sometimes you want to compute the KV and save that, and pass that to the next attention calculation. And you always that's why you hear about the KV cache, whatever. That you need to save the KV. You do not want to compute that every time. So basically, that's the if you think about architecture, the dependency, you realize that it never changes once you calculate the key. So this one, then you have to modify this program, this one for the decoder to use a pre-computed key. Okay. Anyway, that's all. So next time we'll continue with the transformer. Now we are looking at the most important part of transformer, attention. We'll talk about the other components next time. Yeah, and then we are done. Okay. I think there's one question, maybe. Okay, yeah, I think you're. Oh, why is the nonlinear in cross? Where is the nonlinear? Comes from the encoder. How it contains semantics decoder. Cross attention is only to do with encoder. There's a decoder also have both self attention for decoder itself. It uses information of the source from the cross attention. Yeah, so this is basically they treat that separate. So nonlinearity, there's it's actually used in the FFN, which we'll talk about next time. That is a real nonlinear time. Here is more about memory retrieval. So for the attention, it's because V is linear, so somehow it's a little bit more like linear, but with a different attention to focus on different parts. But we will come back to the next exam. Grades will be coming out, I think, yeah, probably tomorrow or certainly before the Wednesday. Yeah. We'll do a curving, so even you are concerned, it hopefully it's not too bad. Okay, yeah. Anyway, that's all.